In this lecture, we'll look at the state space formulation. So in the last lecture, we looked at the concept of feedback control. So before that, in the portion on dynamics, I had showed you that any rigid body or a multi-rigid body system will have a natural dynamics. So whenever we apply some external forces or moments, it would behave according to the Newton's law or Euler's equation. In the concept of feedback control, I showed you that we can achieve a desired trajectory in spite of internal parameter change and external disturbances. So basically, even though the natural dynamics says something, using the concept of feedback control, I could make it follow a desired trajectory, which is not necessarily the same as the natural dynamics. I also showed you that we could use feedback control to stabilize an unstable system, or we could use feedback control to improve the performance of a system. So we started with equations of motion, non-linear equation of motion, using an example of a DC servo motor rotating a link. Then I showed you that we could use Laplace transform to convert it into S domain. So basically ordinary differential equations became algebraic equations in S, and then we could define the concept of a transfer function, which was the ratio of the output to the input, and we could represent these transfer functions in a pictorial form, in a geometrical form using block diagrams. And with this example of this DC servo motor rotating a single link, I showed you that we could ensure that the rotating link follows a constant speed or some other desired trajectory, okay, in spite of changes in internal parameter changes or some external disturbance. So the output in a closed loop feedback control system would be very close to what we want as a desired trajectory. So in this lecture, we'll go back to the state space equation, which are obtained from the dynamics of the rigid body or a multi-rigid body system. We will show you that we can linearize these nonlinear ODEs and then obtain state space formulation. So let us look at a broad classification of dynamical systems. So dynamical systems, basically systems with changes with time, can be described by a partial differential equation, or it could be described by ordinary differential equations. So in our case, for multi-rigid body system or even a single rigid body, we had ordinary differential equations. The ordinary differential equation can be of three kinds. One is called SISO, which stands for single input, single output systems. We could also have SIMO, single input, multi output systems, and then the most general case of multi input, multi output system. The ordinary differential equation also could be linear or nonlinear. So if they are nonlinear, we could have time varying or time invariant. If it is time varying, then the state equations can be written as x dot is equal to function of x, u and t. U is an external input. T is explicitly time. So sometimes these equations have time explicitly in them. We could also have what is called as an output equation, which is y is h of u comma t. If it is a time invariant nonlinear system, then x dot is a function of x and u, and y is a function of u alone. There is no explicit dependence of time in these equations. As I said, we could also have ODE, which represents a linear system, and again in linear system we can have time varying or time invariant. So if it is a time varying linear system, then we could represent the state equations in the form of x dot is equal to f of t. So this function, this matrix contains functions which are functions of time and into x plus g of t into u. Okay, and the output equation will be y h of t into x plus j of t into u. So basically what I'm trying to show here is that these coefficients which multiply x and multiply u and multiplying again x in the output equation, they could be themselves functions of time. If you have a time invariant linear system, okay, these are also called LTI systems. So then we could describe this LTI systems by this kind of differential equation, which is x dot is equal to f of f into x plus g into u, and the output equation y is h into x plus j into u. Okay, so in this case f, g, h and j are constants. They are not functions of time. So as I mentioned, SISO means single input single output system. SIMO means single input multi output system. MIMO means multi input multi output system. So in this lecture, and in fact in most of the course, we will primarily be concentrating on LTI systems, linear time invariant systems. If you want to study linear time varying system or general nonlinear systems, there are advanced courses in control which you need to look at. So let's look at an example of linearization. So we have this simple example of a pendulum. So we have this rod, a massless rod with a mass at the end, and it is rotating about this z axis. So the rotation angle is theta from the vertical. There is also a gravity which is acting here, and we will also assume that there is a torque which is acting at this joint. So there is a motor which is applying this torque. So the nonlinear equations of motion for this pendulum, if you write it in the state space form, we can write it as f x dot equals to f of x comma u. Okay, and if you want to linearize these nonlinear first order differential equations, we have to linearize about a point. And which point do we choose? Most of the time we will choose, or the standard approach is to use linearization about an equilibrium point. Okay, and how do we find the equilibrium point? The equilibrium point is obtained by setting u, which is in this case torque, equal to 0, u of t 0, and then we solve f of x equal to 0. So this is a nonlinear algebraic equation. Okay, so the solution of a set of nonlinear algebraic or transcendental equations will give me x. Okay, and these are the equilibrium points. So this could be any algebraic or transcendental equation. At least conceptually we can solve them. Okay, and we find all x such that f of x equals to 0, and we can have more than one equilibrium point is possible. So again, the example of the pendulum. So the equation of motion of the pendulum is theta double dot plus g by L sine theta is equal to tau by ml square. Okay, and we will call this as u of t. So if you use state variables x1 and x2, x1 is theta, x2 is theta dot. So my state variables capital X is x1 comma x2. It's a 2 by 1 vector. So in state space form, we can have x1 dot is equal to x2. x2 dot is minus g by L sine x1 plus u of t. Okay, so this we have done earlier, and I'm just repeating it, that we can derive the first order equations from the second order equation by using x1 as theta and x2 as theta dot. So continuing with that example of a simple pendulum, we want to find the equilibrium point for those state equations. So hence the first step is we assume or set ut equal to 0. So then the function on the right hand side will be equal to 0 when x2 is 0 and x1 is equal to 0 or pi. Okay, so if you linearize about x1, x2, 0 comma 0, basically we have to substitute sine theta is equal to theta, and then the two first order differential equations can be written in this form. X1 dot, okay, is x2. Remember, it was written in the previous slide, and x2 dot will now become minus g by L into x1 plus u of t. Okay, it was g by L into sine theta, but then theta is same as x1, so minus g by L x1 into x2, and this is 0 comma u of t. So this is the F matrix and this is the G vector in this case. If you want to linearize about pi comma 0, remember x1 could also be pi, and pi is what? It is standing vertically upwards. What is x1 equal to 0? The pendulum is hanging down. So in that case, if you linearize about pi comma 0, then what you will get is sine pi plus theta, which is minus sine theta, and you will get minus theta. For small theta, sine theta is same as theta. So then the first order differential equations or the state equations are x1 dot is equal to x2, that one doesn't change, and x2 dot is now plus g by L x1 plus u of t. Previously, when the pendulum is hanging down and when theta is 0 and you are linearizing about the hanging down position, then it is minus g by L x1. In this case, it is plus g by L x1. So in general, what can we do? We can use Taylor series. Okay, so instead of simply saying sine theta is same as theta and doing this simple things, we can formally linearize any differential equation using nonlinear differential equation using Taylor series, and again we linearize about an equilibrium point. So let's assume that we have a set of nonlinear differential equation x dot is equal to f of x comma u, where x now is an n by 1 vector, u is an m by 1 vector, so the number of inputs could be less than the number of states. Okay, so x is an element of Rn and u is an element of Rm. So we are going to linearize about an equilibrium point, and what is the equilibrium point? All x comma u such that x dot is equal to 0, or which implies all x comma u which satisfies this vector nonlinear set of equations f of x comma u equal to 0. And again, these are nonlinear algebraic or transcendental equations. So you can have more than one solution for f of x comma u equal to 0. Okay, so basically we can have more than one equilibrium point, and so we need to linearize about a chosen equilibrium point. So let x e comma u e denote an equilibrium point we are interested in. So we can expand this right hand side using Taylor series about xc comma ue. Okay, so what is the expression for Taylor series? So any one of these functions, so let's say fi x comma u can be written as fi xc comma ue plus partial of fi with xj and j equals 1 through n, evaluated at x equals xc and u equals ue into delta x. Okay, so this is the first term in the expansion of the Taylor series. And what is delta x? It is xj minus xj equilibrium point. We can also look at the partial of fi with uk, because remember there is a x and a u. So again we have k equals 1 through m summation partial fi with uk. Again this is evaluated at x equals xc and u equals ue multiplied by delta u, and delta u is again uk minus uke, and then plus we have order 2 and order 3 and all the higher order terms. So we are going to drop all the higher order terms, and this term is also equal to 0, the first term, because why? This is the definition of an equilibrium point. So Fi of xc comma ue must be equal to 0. So what you are left with is one part which is partial of Fi with respect to xj into delta x, and then partial of Fi with respect to uk and delta u. Okay, so both of these terms can be written as some x tilde dot is equal to some matrix into x tilde plus some matrix G into U tilde. So what is the dimension of x tilde? It is n by 1 because there are n of these state variables. So what is the dimension of f? It is n by n. And what is x tilde? So x tilde and u tilde are nothing but x minus x equilibrium, u minus u equilibrium. So it is the small deviation about the equilibrium point. Okay, so what is the dimension of G? It is n by m. Remember, u is an element of Rm. So there are m inputs and n state variables. X is n dimensional, u is m dimensional. So now we have G into u tilde. So this is n into m and m cross 1. Okay, so these are the state variables, element of Rn. And what are these matrices? They are nothing but the partials of function Fi with respect to xj evaluated at xc and ue. And what are the elements of G matrix? This is partial of Fi with respect to uk, again evaluated at xc and ue. Similar to the state equation, we can also look at the output equation. And here we are going to assume that y denotes the output. It is also a vector, but there are only p of them. So the number of state variables are n, the number of u is m, and the number of measurements or output variables are p. Okay, and p will be less than or equal to n. So again, we can use Taylor series and expand this nonlinear equation about xc and ue. So similar to the state equations, we will get some y tilde is equal to some matrix into h into x tilde plus some matrix j into u tilde. And what is ye? Ye is the equilibrium point, which is the function h evaluated at xc ue, and y tilde is y minus ye. Okay, so what is this elements of the H matrix? So Hij can be written as partial of Hi with respect to xj and again evaluated at xc comma ue. The elements of the J matrix here can be obtained as partial of Hi with respect to uk, again evaluated at xc So what are the dimensions of y? Remember, it is p of them, so this is clearly p cross 1. How about the dimension of h? It is p cross n. X tilde is n cross 1. The dimension of j is p cross m, and u tilde is m cross 1. So in the rest of the course or in the rest of this lecture, we will drop these tilde. Unnecessarily we are carrying around one more symbol. So we will use x, u and y instead of x tilde, u tilde and y tilde. Remember, x is a vector of dimension n cross 1, u is a vector of dimension m cross 1, and y is a vector of dimension p cross 1. And they are nothing but x tilde, u tilde and y tilde. We are just going to drop these tilde from the rest of the treatment. So in summary, we can obtain the state space formulation of a linear time invariant system in this following two sets of equations. One is called as the state equation, which is x dot is equal to f into x plus g into u. X is an element of Rn, u is an element of Rm. And then we have an output equation, which is y is equal to h into x plus j into u, and y is an element of Rp. So this is x is, again to repeat, are the state variables. It has dimension of n cross 1. U are the control inputs, which has dimension of m cross 1. Y are the output or the measured outputs, and this has dimension of p cross 1. So let us continue. One of the most basic issues in state space formulation is that state variables are not unique, and I will show you an example. Again, we will use this planar pendulum. So now we have this pendulum with a mass which is oscillating here with an angle theta. Gravity is this way, and we had chosen the two state variables x1 and x2 as theta and theta dot. Okay, we could also use another set of state variables which are x1 tilde and x2 tilde. x1 tilde is defined as omega 0 into theta, and x2 tilde is same as theta dot. So x2 tilde is same as earlier x2. However, x1 tilde is a scaled version of the previous x1. And what is omega? It's omega square is g by L. So now if you obtain the state equations, you will see that you will get these following state equations, which is x1 tilde dot will be equal to omega 0 x2, and x2 tilde dot is minus omega 0 square sine of x1 divided by omega 0 plus u2. Again, if we linearize about 0 0, we will get x1 tilde and x2 tilde. So this is like x dot. F matrix now will be 0 0 omega 0 minus omega 0, x1 tilde x2, and 0 and 1 u of t. So you can see that the F matrix has changed. In the initial F matrix it was 0 1 and then something like minus g by L and 0. Okay. In general, we can have another set of state variables z, and let's assume that z and x are related by this transformation. X is equal to some p times z, and it is a linear transformation, meaning that this p is constant and this p matrix is full rank. So p is invertible. So x is n by 1, so z is also n by 1, and this p is n by n matrix, and it is constant elements and it is invertible. So now in terms of z, we can write the state and output equations in this form. So basically we had x dot is equal to fx plus gu. Now we have x is pz, so we have p into z dot is f into pz plus g into u. Remember, p dot is 0. So if you were to worry about what happened to when you did x dot, should we get a p dot into z? No, that term is 0. So x dot will be p into z dot, which is what is here. And likewise, we have y is h into p into z plus j into u. So we could rewrite these state and output equations as z dot is p inverse f p z plus p inverse gu, and y is h p z and then j into u. Okay, remember p is invertible, so p inverse exists. So the first basic question is, how do we know that both these systems are same? Okay, so if you are an analyst somewhere which you are using x as your state variables, okay, you would have got x dot is equal to fx plus gu. If you are another analyst somewhere else and you are using z as your state variables, then you will get z dot is p inverse f p z plus p inverse gu, and the output equations are now y is h p z j u. So it is not clear, and remember these are all numbers, it is not clear that we are describing the same system. Okay, So what is common between this description using Z and the previous description of the state equations and the system using X? So let's continue. So what is common between F and P inverse FP? Let's start with that. So one important thing that if you have studied linear algebra, you can look at the eigenvalues of this F and P inverse FP. Okay, so what is the eigenvalue problem? We have to solve a characteristic polynomial which comes from setting determinant of lambda I minus P inverse FP equal to 0. Okay, so I is the identity matrix. So this we can simplify as determinant of lambda into P inverse P. I could be written as P inverse P minus P inverse FP equal to 0. And again we can simplify again and we can write this expression as determinant of P inverse lambda I minus F. So basically we'll take P outside and then we'll have P inverse lambda I minus F into P equal to 0. So the determinant of a product of three matrices are the determinant of each one of these three. Okay, so we can write as determinant of P inverse, then determinant of lambda I minus F, and then determinant of P equal to 0. So this itself can be simplified because now these are scalars. So we can take determinant of P inverse and then we can go back and put this on this side. So you'll get determinant of P. So P inverse P is identity matrix. So you are left with determinant of lambda I minus F equal to 0. Okay, so what have we showed you? That the eigenvalues of P inverse FP is the same as the eigenvalues of F. Okay, so this is called as similarity transformation. So if these eigenvalues are distinct, meaning there are n eigenvalues of F, and let's assume that lambda 1, lambda 2 all the way to lambda n are the n eigenvalues, and if they are not equal to each other, then you can obtain P such that P inverse FP is a diagonal matrix. So this is a diagonal n by n matrix and each of these diagonals are lambda 1, lambda 2 all the way to lambda n. So how do I find out what is P? Firstly, P is an n by n matrix because we are doing P inverse F into P. So all of them are n by n matrices. So there is a very nice formula to obtain P. This is called as the van der Waals matrix. Okay, you can look at this very good book on linear algebra by Golub and Van Loon. So what it says is to obtain this P, we put in the first column 1 lambda 1 square all the way till lambda 1 to the power n minus 1. Second column is 1 lambda 2 square all the way till lambda 2 to the power n minus 1, and the last nth column is 1 lambda n, then lambda n square, lambda n to the power n minus 1. And remember, we are discussing the case of lambda 1, lambda 2 all the way till lambda n are distinct eigenvalues. So if you were to use this matrix P, then P inverse FP will be a diagonal matrix with lambda 1, lambda 2 all the way till lambda n on the diagonal and all other elements are 0. If lambda 1 is equal to lambda 2, so let's say two of them are repeated, then the P matrix can also be determined. In the first column of the P matrix is 1 lambda 1 square, lambda 1 to the power n minus 1. Then the second column is, which is corresponding to lambda 2, is 0, 1, 2 lambda 1 all the way till lambda 1 n minus 1 into lambda 1 to the power n minus 2. So basically, how did I get this second column? It is the derivative of this first column. And since we are only considering two of them repeated, the rest of the matrix remains same. The nth column is 1 lambda n all the way till lambda n to the power n minus 1. Now, if you compute this P inverse Fp, what you will get is lambda 1, 1 comma lambda 1 in the second column, and again 3, 4, 5 all the way till n are distinct. Okay, so it is not exactly a diagonal form, but this is the best that you can do. This is called as the Jordan canonical form. In the Jordan canonical form, and in this example, there are only two repeated eigenvalues. You will have first column is lambda 1 0 0 0 all the way. The second column is 1 lambda 1 0 0 0 all the way. The third column is 0 0 lambda 3 zeros, and so on. So while you are solving this eigenvalues of a matrix, you can also get complex and eigenvalues. So we can have a lambda 1 which is a plus ib. So the second eigenvalue will be a minus ib. This is a property of complex numbers. So one of them is an eigenvalue which is a plus ib. The other one must be a minus ib. So in that case, if you do P inverse Fp, then what you can see is you will get AB minus BA, and again, since we are taking only two of them are equal, then you will have lambda 3 all the way till lambda n, and all this off diagonal terms to be 0. So this is the best we can do if you have complex conjugate eigenvalues. Of course, there could be more complications. You can have many of these eigenvalues equal. So if there are three of them equal, then you will have some things which is happening in the first column of the P, the second column of the P, the third column of the P. The third column is the derivative of the second column is the derivative of the first column, and so on. So you will have some more complications. So it will not be exactly diagonal, but it is still a Jordan form. You can also have repeated complex eigenvalues. Okay, so you can find out what happens when you have a repeated complex eigenvalues, what happens to P inverse Fp. So this diagonalization or this Jordan canonical form, these are very useful for state space formulation. Okay, so we will see that in the next few slides. For more details on this diagonalization or Jordan form or complex eigenvalues, you should look at a modern or a good textbook on linear algebra. So one such recommended textbook is by Strang, or you can also go back and see Golub and Van Loan. So let's go back to state space formulation and transfer function. Okay, so let's consider an ODE, and in particular a single input, single output system. The ODE is given in this form. So the third derivative of y with time plus 6y double dot, this is the second derivative of y, plus 11y dot plus 6y is equal to 6u. So this is my ordinary differential equation which is describing a single input, single output system. So if you were to use Laplace transform on this, so what will you get? So the output is y of s, input is u of s. So this will be some s cube into y. This will be 6 s square into y. This will be 11 sy, and this is 6y. Okay, all the initial conditions are 0. So whenever we take Laplace transform, we assume that the initial conditions are 0. So what is the transfer function between y and u? It is 6 divided by s cube plus 6s squared plus 11s plus 6. Okay, so I have chosen this example because we can now very simply do a partial fractions of this. So if you go back and remember what is partial fraction, we can write this as some a divided by s plus something plus b divided by s plus something and c divided by s plus something. So it turns out it can be written as 3 divided by s plus 1 minus 6 divided by s plus 2, 3 divided by s plus 3. So this transfer function y of s divided by u of s can be written as sum of these three fractions. So in the block diagram form, I can represent this in the following. So what do I have? I have an input which is u of s and output which is y of s. So first thing you can see is this is multiplying by 6 u of s, and then so 6 u into u of s is given by all these terms. So you have 6 into u of s is ys into all this s cube plus 6x square plus 11s plus 6. Okay, so that could be written in this way. So what do we have here? So you have a block which is 1 by s. This is called as an integrator. Okay, remember Laplace transform of y of 1 by s into something is nothing but the integration of that quantity. So we have 1 by s, and the output of that you multiply by minus 6. Okay, and then you put it back here. Then you integrate again, and then the output of that you multiply by 11, minus 11, and put it back here. And final output of this you integrate and you multiply it by minus 6 and you push it back here. So basically what are we doing? We are finding that 1 by s into 6 plus some 11 into s, an integral, and then minus 6 into s. So we are putting back all these things here, and then if you sum it up, then you will get these. Okay, so this is a block diagram form of this transfer function. So let's look at the state space form of that equation. Okay, so this is the third order ODE. So there are 3 state variables. So first equation is x1 dot is x2, x2 dot is x3, and x3 dot is minus 6x1 minus 11 x2 minus 6s3 plus 6u. And what is the output variable? That is x1. So we can rewrite these 3 first order equations as x dot is equal to fx plus gu. So what is x here? It is 3 by 1. It's a vector of x1, x2, x3. So x dot is x1 dot, x2 dot, x3 dot. That is equal to f into x. Okay, so what is the first row of x? That you can see from this equation. So x1 dot will be nothing but x2, which is 0, 1, 0 into x1, x2, x3. So this will be the 1 here. The second equation is x2 dot is equal to x3. So what will be the second row of f? It will be 0, 0, 1. And then the third equation is x3 dot is this minus 6x1 minus 11x2 plus minus 6x3 plus 6u. So this is minus 6 into x1 minus 11 into x2 minus 6 into x3. And what is the rest of it? What will be g? U here is only 1, right? So there is only 1 input and 1 output. So this is a single input, single output system. So g will be 0, 0, 6 into u, because remember there is a 6u term. And how about the output equation? Y is equal to hx. So what is the single measurement we are doing? A single output, which is x1. So it is 1, 0, 0 into x. Okay, so y is 1, 0, 0 into x1, x2, x3. So basically y is equal to x1. So the eigenvalues of f are obtained by solving determinant of f minus lambda I equal to 0. So this is f is a 3 by 3 matrix. So the characteristic polynomial would be cubic, and it turns out when you expand, when you put all the value, whatever is f there, all the elements of f, you will get lambda cube plus 6 lambda square plus 11 lambda plus 6 is equal to 0. So the characteristic polynomial is same as the denominator of the transfer function. This is a very, very useful observation. And what are the roots of the polynomial? They are lambda 1 is minus 1, lambda 2 is minus 2, lambda 3 is minus 3. So these are distinct roots. Okay. So hence we can find P using that Vandermonde matrix. So remember, the first column was 1, then lambda 1, then lambda 1 square. Second column was 1, lambda 2 square. Third column was 1, lambda 3 square. Okay, so lambda 1, lambda 2, lambda 3 are given here. We can compute lambda 1 square, lambda 2 square, lambda 3 square and all the terms, and we will get P, which is this. P inverse can also be calculated. This is a reasonably simple matrix, and you can also go back and use MATLAB. So if you type this matrix in MATLAB and say I want the inverse of this P matrix, you will get back this. So the inverse of P has first column 3 minus 3 1, second column 2.5 minus 4 1.5, third column 0.5 minus 1 0.5. So as I said, let us choose a new state variable z, which is x equals p times z. So the state equations in terms of z are z dot is p inverse fpz. Go back and see the formulation, and then p inverse gu. So what do we get? We know what is p, we know what is f, so you can substitute and we can do some simplification. Okay, then you will get z1 dot, z2 dot, z3 dot, and what do we expect? We expect it to be diagonal. Remember, P inverse Fp will become a diagonal matrix. That was the purpose of finding that P matrix. So Z1 dot will be equal to minus Z1 plus 3 into U. Z2 dot is minus 2Z2 minus 6 into U, and Z3 dot is 0 0 minus 3 Z3 or 3 minus 3 Z3 plus 3 into U. And how about the output equation, which is y is equal to h into p into z. Again, p is, we know that. So what you will see is, if you simplify this, you will get 1 1 1, this into this is 1 1 1 into z1 z2 z3. So what have we got? So we had one form which is x dot is equal to fx plus gu, and now we have another form which is z dot is equal to some matrix times z plus some other matrix times u, and likewise we had y is equal to hx. Now we have y is some matrix times z. So let's write this transfer function in a block diagonal form. Okay, so now what you have is u, which is coming in, and then you can see that you have to multiply u by 3 minus 6 and 3, and then whatever is the output here you integrate once and you will get z1, and then you feed back minus 1. Similarly, whatever you do integrate once, you will get z2, and then you whatever you have you integrate here, output of this input, and you will get z3. And then when you add z1 plus z2 plus z3, you will get y of s. Remember, y is 1 1 1 into z1 z2 z3. So in general, if you have a system, okay, which is x dot is equal to fx, okay, and then you have y is equal to hx, okay, so plus ju, okay, so we have x dot is equal to fx plus gu, and y is equal to hx plus ju. We can also write it symbolically in a block diagram form. So this is the block diagram representation of the state equations. So what do we have? We have u, which is coming in. So this is g into u. Okay, and then we also need to add f into x. So we will get x dot, which is f into x plus g into u. And how do I get x here? That is the integral of this x dot. So that is what is shown here. You will have a 1 over s. Actually, there are, if it is a vector, you will have n parallel integrators. So each of those x dots needs to be integrated, and you will get one x. You multiply by f, and then you add to gu, you will get x. So this is the feedback part. The output of this integrator is x, so you can multiply it by h, and you also need j into u. So you take this u, which is input, directly multiplied by j matrix, and then you add these two and you will get y. Okay, so this is a nice way to represent what is happening in the state equations. So if you just have state equations like this, which is x dot is equal to fx plus gu and y is equal to hx plus ju, then you don't see this nice structure that there is some integration which is happening. Input to the block is x dot, output after integration is x, and then you can feed back. Okay, so the state space formulation, which is this, can be obtained directly from the equations of motion. Okay, remember, even if you have a nonlinear equation of motion, you can linearize about an equilibrium point, and then you will get this x dot is equal to fx plus gu and y is equal to hx plus ju. So this term j into u is also sometimes called as the direct term. So whatever is the input, it is directly going to the output. It is not going through the plant. Nothing is happening. No integration or some other feedback is happening to the ju term. So for most single input, single output system and j of u equal to 0, we will have x dot is fx plus gu and y is equal to hx. So we can also think of this as you can take the Laplace transform of this ordinary differential equation. It's a vector set of vector equations, but we can take the Laplace transform and we can write it as s into x of s minus x0. So let's keep the initial conditions for a while. This f is a constant matrix into x of s plus g into u of s, and the output equation can be written as y of s is equal to h into x of s. So both of these two can be now written in a simple form after some manipulation as y is equal to h into what is x? X is si minus f inverse x of 0 plus h into si minus f inverse gu of s. So think about it, that we want to rewrite this, we have to take x this side, so you will have si minus f, and then you will have something which is multiplying x of 0 and something which is multiplying u of s. So for 0 initial conditions, which is x of 0 is 0, then the transfer function is nothing but y of s divided by u of s. Remember, now we are looking at single input, single output system. So y is one dimensional, u is also one dimensional. So this same expression here, y of s divided by u of s, you drop this term which is x of 0. So what do we left with is h into si minus f inverse into g. So the transfer function of a state equations, which is of this form, x dot fx f into x plus g into u, and y is h into x plus j into u, for a single input, single output system with initial condition 0 is h into si minus f inverse into g, and this can be written as adjoint. So the inverse is nothing but the adjoint divided by the determinant. So we have h into the adjoint of this matrix into g divided by the determinant. So in summary, control is a very vast area. Okay, we have linear system, nonlinear systems, linear time in varying system, linear time varying system, SISO system, MIMO system, all kinds of classification of dynamical systems we have. It is a very vast area. We were primarily interested in linear time invariant systems. We can obtain the state equations of motion, state space equations of motion from the dynamics of the system. They can be linearized about an operating or equilibrium point. And then we get these matrices F, G, H, and J. Okay, so these four matrices are sometimes called as the state space realization of a linear time invariant system. If this was a function of time, this is also a function of time, H is a function of time, then you'll have linear time varying system. Okay. And I showed you there is a relationship between the state space formulation and the transfer function. So the transfer function for the SISO system, y of s divided by u of s, is nothing but h into some si minus f inverse into g.